Here is an example of the Cartesian product, two examples of Cartesian product, it is infinite and finite ones. So, then we define functions, function from a set x to another set y is a mapping that map every element of x, the domain, to exactly one element of the codomain. So, a function f from a to b, yeah, now tell him, a function f from a to b maps every element of a to exactly one element of b. Okay, the a is called the domain of here x is called the domain of the function, y is called the codomain of the function, and the mapping is x, the element x is the pre-image, and the element of y, which is the mapping, is called the image. Okay. Okay, so this we talked about it last time. Okay, I am just going to give you a quick review for. This is another way of looking at function. A function from x to y can be thought of as a collection of those ordered pairs where the pre-image and image ordered pairs, right. So, list all the elements of x, and wherever their images are from elements from y, you just list them. So, how many elements will be there in this this collection of ordered pairs? What will be, so is this clear? If this is just basically the function representation is a collection of ordered pairs. So, how many elements will be there? How many ordered pairs will be there in the function?
Cardinality of set x.
Cardinality of set x multiplied by cardinality of set y.
Just the same number as the next.
The cardinality of x, okay. The cardinality of x will be the is actually the number of ordered pairs I will give. Each element of x is mapped to exactly one element of y. So, if I just list who is x1 mapped to, who is x2 mapped to, who is x3 mapped to, I will get exactly the cardinality of x list. Okay. So, this way of looking at function, the reason we are looking at it now this way, because the next definition is just drops that restriction. Okay. So, a function from x to y is a subset of x cross y. Subset of the Cartesian product, all possible ordered pairs, that particular subset which has this restriction that exactly in every order, exactly one ordered pair contain a given element of x. Okay, no more than 1, no more than 2, and no less than 1. So, a relation is basically just anything with no restriction, just take any subset of x cross y, maybe the empty set, maybe the whole x cross y, maybe half of it, maybe a function, may not be a function or something. Okay. This a subset of x cross y is called a relation. Okay. So, a binary relation is a subset of x cross y. There are two sets x and y, so we call it binary relation. A ternary relation would be a three-array relation will be a subset of x cross y cross z, right. There are three sets. General n-array relation would be a subset of a1 cross a2 cross as many as we have. These sets a1, a2, a3 or x and y, these are called the domains of this thing. In functions, there are exactly two sets involved, one set and then the images set, right, the possible images set, the possible inputs, possible outputs. Those sets could be complicated objects, but it is nonetheless one set, and we had the name, the domain and codomain. Here these are all are called domains, or the number of domains is called the degree of the relation. Okay. So, binary relation has degree 2 and higher order relation. This is what we saw, this is what we call database or a relation, a table, in that sense the relational database word we remembered. So, this database, this table is actually a subset of the set of all possible names cross the set of all possible IDs cross the set of all possible departments in LUMS or in whatever context we are talking about, or the set of all possible numbers between 0 and 4.0. right. That will these this particular subset of it containing 5 elements is a relation, right. What is the degree of this relation? What is the degree of this relation? 4. Why? What is another name of the degrees? Columns or fields or attributes, right. And what is the cardinality of this relation? What is the cardinality of this relation? Cardinality, it is a subset, right. So, what is the cardinality of this subset? Sorry? 5? Yes, because there are 5 rows, that is cardinality of this relation, right. Make sense? What is the type of each element of in this database, in this relation? Like what kind of, is it a single number or 5 numbers or what is it?
4 tuples.
It is a 4 tuple. If an ordered 4 tuple, the first element is from the set name, the second coordinate is from the set ID, the third coordinate is from the set CGPA and so on. Okay. This also we saw, I just don't talk about it, I just deleted it, but then copied the old version. Here is a relation from the set of students, it is a subset of the set of possible students and the set of courses, right. It is a subset of that, students cross courses, and this represents the registration, the Zambil record of students, right. Remember, it looks more like a function. We represented function as a bipartite graph. On one side the domain, on the other side the codomain. This is a binary relation. We can make it represent it with this same type of bipartite graph. On one side one domain, the other side another domain. If x is related to y, we add a line between them. Okay, if the particular pair is there. So, this is a relation. Is this a function? Is this a function? Yes or no? Yes. Why not?
Because A is mapping on into D, M and calculus.
Yes. So,
It has 2 codomains.
no, you are right, but it is not codomains. No, it has 2 images. It is not even a function. It is attempting to have 2 images. F is A is going. If it was a function, then A would have been mapped to 2 elements, DM and calc. Even serious problem, E would not have been mapped to anything. Every element of the domain has to be mapped to exactly one element. It was not a function, but it is a relation, right? And that is exactly we saw the definition. Function had certain restriction. A subset of the ordered pairs, subset of the Cartesian product, the cross product with certain restriction. Relation has no such restrictions. Okay? You can leave out people from being related to anything. You can have C to be related to many items, right. This is a terminology. Say the example, set X in the set courses. I think it is the same example as we saw on the diagram earlier. The way we say it is, we say ADM is an element of the relation. R is the relation. A comma DM, this ordered pairs A comma DM is an element of the relation. Okay. Of course, DM comma A is not, it is an ordered pairs. Okay. So, this ordered pair is part of R, or sometimes we write A is related to DM. So, in old text it is written as A R DM. Okay. In more classical formal text could be written like this, it is a predicate R ADM is true or false, right. So, if ADM is in an element of that subset, which represents the relation, then it will be true, otherwise it will be false. So, in the previous example, B calc is not in R, right. Here you see, you won't see B calc ordered pair. A and C are related to 2 elements of Y, and that is not a problem, we talked about that. This is the example. It works for these kind of things, right. So, it's a very, that's the database, the whole database theory is going to be, is based on this thing, okay, database, the DBMS and database administration and database management, okay. It represents all of this stuff. Okay. So, this is what we talked about. A binary relation is a subset of A cross B, X cross Y, if these are the 2 domains. These X and Y need not be distinct, right. So, a relation can be made from as a subset of X cross X, okay, or Y cross Y. In that case, we generally call it a relation on the set, not the relation from x to y, right? A relation on the set. So it's just a subset of x cross y, x cross x, you see y is equal to x, and that's called a relation on this. So we'll today talk about some properties of the relation, okay? So last time we didn't reach any ICP, right? Okay. So I have a set A, and I'm going to define some number of relations on different sets. So here is one relation. The relation relates two numbers in A, x, y. If x is a factor of y, if x divides y, if x is a divider of y. Does it make sense? Okay. So look at the example. Is 1 part of the R is an element of R? Why is 1 an element of R? Because 1 divides 1, right? 1 is a factor of 1. Is 1 2 an element of R? Because 1 divides 2. Is 2 3 an element of R? 2 does not divide 3, so it's not an element. See, simple set theory, we know everything, membership predicate, some criteria, some element will go to set, some won't go to set. So 2 3 isn't in R. Okay? Then some more questions. Is 3 6 in R? Is 4 6 in R? Why not? 4 6 is 4 does not divide 6. How many elements are there in R? Why? Count कर दिए. Okay. So yes, count कर लो, and then you will see the number of, that's cardinality question. Cardinality is the number of elements, so we just find out this thing, right? Here is a representation of this thing. 1 divides all of these 5 numbers, right? There are 5 numbers here. 1 divides all of these 5. 2 divides itself, and 4 and 6, the even of them. So that's 8. Okay? Yes, 8. And 3 divides itself and 6, right? And 6 divides itself, and 4 divides itself, and so yes. What? Yes.
सर ये जो relation आ रहा है, it's a relation of A, उसके अलावा भी
It's a relation on the set A.
इसी relation को हम किसी और set पे भी apply कर सकते हैं.
No, its relation is given on the set A. It's defined on the set A. Yes? Sorry? Count the number of lines. I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. Okay. So, okay, here are certain, sorry? I don't know, you should have counted there, whatever was in the slides. Count the relation, here are certain relations on the set of integers, right? Positive, negative, all integers. R1 is the inequality relation or the less than equal to relation. Any number is related to all other integers that are are greater than or equal to A, right? A is related to all numbers that are bigger than A. So, is this relation, is 1 part of R1? Is 1 an element of R1? Why? Why is 1 an element of R1? Why? Because 1 is lesser or equal to 1, right? So, the criteria of the relation says that if it's A is less than or equal to B, then I should add AB to the relation. So, is 1 2 an element of R1? Quickly, is 1 2 an element of R1? Because 1 is less than or equal to 2. Is 2 1 an element of R1? Why not? Because 2 is not less than or equal to 1. That's a better way of saying it. 2 is not less than or equal to 1. Is 1 negative 1 an element of R1? Why? Because 1 is not less than or equal to 1, negative 1. 2 2 2 is less than or equal to 2, so it should be there. R2 relates elements and number A to all numbers that are bigger than that are smaller than A, right? So it relates A with numbers that are smaller than A. So is 1 1 an element of R2? Is 1 1 an element of R2? No, why not? Huh?
1 is not greater than
1 is not greater than 1. Is 1 2 an element of R1, R2? No, because 1 is not greater than 2. Is 2 1 an element of R1, R2? Is 2 1 an element of R2? Is 1 negative 1 an element of R2? Is 2 2 an element of R2? Now, okay. So let's see R3. Now you have to write the rest of them. R3 is those elements. So AB, if A is equal to B or A is equal to negative B, right? So it's called the absolute value relations, right? So if A is equal to the absolute, if A is the absolute value of B, or if A and B are absolute values of each other, or oh no, if A is equal to the absolute value of B, then we relate them, right? Then they are part of, those pairs are part of the R3. So is 1 1 an element in R3? Quickly. 1 1 in R3 or no? Is 1 2 in R3? Is 2 1 in R3? Is 1 negative 1 in R3? And 2 2? Yes, right. So this is absolute value relation. R4 is the equality relation. It just relates two things that are equal, right? So this is going to be important for the in the session tomorrow. Called the equivalence relation. This is equality relation. Things are equal if they are equal, then they are related. Okay. So is 1 1 in R4? Is 1 2 in R4? Is 2 1 in R4? 1 negative 1 and 2 2? Yes. And R5, it's a successor relation, right? If A is a successor of B, then they are related, right? If A is a successor of B, then A, B are related, right? So then A is related to B in the order thing, in this order. So is 1 1 in R4? R5. Is 1 1 in R5? No, because 1 is not equal to 1 plus 1, right? If 1 2 in R5, like because 1 is not equal to 2 plus 1, right? That condition isn't true. Is 2 1 in R5? 2 is equal to 1 plus 1, right? So 2 is a successor of 1. 1 negative 1? No. It's a double increment, right? So it's the next successor. 1 isn't equal to negative 1 plus 1, right? Yes, please. So what can I do? Can you call this guy, please? The screen staff. There is something. Yeah, I can also see it. Okay, so is what were you talking about? Please stop talking. R5. Is 2 2 in R5? No, 2 is not a successor of 2, right? 2 is not equal to 2 plus 2. R6. Can you please stop talking? Stop talking, please. R6. How many of you know the equation of circle? So okay, let me just call this thing R6 is what's called the, oh God. So R6 is called points in a circle. Why should we call R6 points in a circle? R6 is actually the circle.
Because all points A and B will be within a certain boundary, which is 3. So you can draw a circle of radius 3 and then be within that.
All points?
All combinations of A and B will be less than 3, so you can draw a boundary at a circular boundary at 3 and then all be within it.
Circle of boundary at 3?
the radius.
Radius.
Basically.
Radius will be 3, square root of 3. Yeah. Okay. So these are basically those points which are, think of a circle, it's center at the origin 0 0 and radius r. Which points are within that circle? So you find which points are on the circle, that is x squared, those points where x minus 0 plus x minus 0 squared plus y minus 0 squared equals 3 squared, right, equal r squared. Those are the points. So if that is less than or equal to, then you are talking about the set of points which make the circle. So these are those points, but this is integers, only some few dots, some grids thing. So is 1 1 in R3, R6? 1 is less than or equal to 1 plus 3, right? Is 1 2 in R6? Is 2 1 in R6? 2 is equal to 1 plus less than or equal to 1 plus 3, right? What am I doing? No, 2 plus 1 is less than or equal to 3. Is 1 negative 1 in R3? Is 1 negative 1 in R3, right? R6. And 2 2 in R6? No, 2 plus 2 is 4, they are not in R6, right? So that's how you do this. See, you know now the relations. This was a quick review of the last thing we didn't do last time. This is now becoming interesting, and when we do based on this, we'll build what's called equivalence relation and what's called partial orders, right? Those are extremely important concepts in computer science. We need it a lot, okay? Math and computer science and physics and everywhere. Data science also, partial orders are used a lot in data science and algorithms. Okay, some properties of relation, right? A relation is a subset of, a relation from x to y is a subset of x cross y. A relation on a set x is a subset of x cross x, okay? If x and y are equal. By the way, the flicker is still there now. So, and it's a binary relation because we are true. So now onward we are going to talk about binary relation. We say a binary relation is reflexive. A binary relation on a set x is called reflexive relation. If for any element a in x, it is related to itself, right? So if a is in R for every element a in X, okay, then we say that the relation is reflexive. Okay. So let's do a few examples. Let's say I have the set A 1 2 3 4, and I have a relation R1 which is 1 1 1 2 2 3 3 3 4 4. Is this reflexive relation? Why not? So she says it's not a reflexive relation because a reflexive if were R1 to be reflexive, it should have had 1 1, which is there, 2 2, which isn't there, 3 3, which is there, 4 4, which is there. So only 2 2 is missing. That's why this relation is not reflexive. Okay? Is R2 reflexive? R1 what? So look at the definition of reflexive relation. For every element in X, it should be related to itself. Every element A in X should be related to itself. So AA should be there for every A in X. Here 2 2 is not there. Yes? Nahi, galat to nahi. It doesn't say which other stuff could be there. Many other things could be there. But these four, in this particular case, these four are required. If those four are present, then they will be, yes. No. So it says for every element A, AA should be there. No. 2 2 is needed. No, 2 2 is not there in R1. Not instead of this. In addition to 2 3, instead of 2 3 is a replacement of 2 3. Those are other things. There could be many other things. I am going to give you some examples, and it should be clear. That has nothing to do with relation. Relation, if R1 was reflexive, those four elements must be there. There could be many others. As long as they are ordered pairs in X cross X, then they should be okay. Okay. So is this R2 reflexive? Why is it reflexive? It does have 2, 3. It could have 3, 2. It could have 3, 4. It could have 1, 5. It could have 1, 7, right? Could it have 1, 5? Could it have 1, 5 and still be reflexive? Yes? It wouldn't be a relation on this set A, right? 5 is not a thing. It has to be a subset of A cross A. Okay. So R2. Yes. Please stop talking, okay? Please stop talking or you leave the room. R3. 1, 1, 2, 2 and 3, 3. Is this reflexive? Why not? 4, 4 is missing, right? All of these 4 have to be present there and they are not, one of them is not there, so it's not reflexive. Okay. A relation is called symmetric relation if whenever there is some element AB, where A is an element of the set X and B is an element of the set X, so then BA is also there. Okay? So if A is related to B, then B is related to A. So some kind of this bidirectionality thing, right? Okay. So that's the definition. Let's do example. Again, the same set A, 1, 2, 3, 4, R1, 1, 1, 1, 2, 2, 1, 3, 3, 4, 4. Is this symmetric?
Yes.
Why is it symmetric? Why is it symmetric?
Because for every relation that we have over here, the opposite version is also.
For every pair that we have, yes, what did he say? 1, 1, 2 बार आना चाहिए. Okay. That's good. Relation is a subset. You can write it as many times as you want. Multiplicity, repetition don't matter, right? 1, 1 is there, so 1, 1 should be there in order for this to be symmetric. So it's already there. 1, 1 and 1, 1 is there, so it's there in the other directions too. Okay. In this particular case, the only requirement would be if because 1, 2 is there, so 2, 1 must be there. Otherwise, it won't be symmetric, right? Or vice versa. 2, 1 is there, so 1, 2 should also be there. Does this make sense? Okay, 3, 3, 4, 4. Just don't impose any further requirement on the relation to be symmetric for this case. Okay, is this relation reflexive, symmetric? Right, 1, 1 is there. Well, 1, 1 should be there, and 1, 1 in the other direction should also be there, and which is okay. It's a relation on a set. If it was a relation from some set to some other set, and this set also had 1 and the other set had 1, now these ones are different. Then 1 of X and 1 of Y could be slightly different things, right? So then we wouldn't be able to say that. But now we are talking about relation on one set only. R3 is this relation 1, 3, 3, 2, 2, 1. Why is this not symmetric? Why is this not symmetric? Okay, yes, so it doesn't have 3, 1, that's good enough a reason for this to be not symmetric. 1, 3 is there, 3, 1 ought to be there for this to be symmetric. 3, 1 isn't there, right? So this is not symmetric. Okay, and otherwise 3, 2, it's required 2, 3 for this to be symmetric. It required 1, 2 also. A relation is antisymmetric if whenever AB is there and also BA is there, right? Whenever there is this kind of bidirectionality, then A must be equal to B. So essentially this bidirectionality is not allowed except for equal things, right? For a relation with itself, that will be there. AA is there in this direction and that direction, right? But if AB is there, then BA cannot be there. This is what it says. Antisymmetry is forbid bidirectional relation. Okay? The other one requires all of them. So they are not the negation of each other. Okay? But antisymmetry and symmetry are not the negation of each other. They're two different requirements. Okay? I'm going to give you examples where. Okay. Is this relation antisymmetric? Why not? Yeah, there is 1, 2 is there, and also 2, 1 is there, and that's it. For whenever this is only allowed for equal things, right? 3, 3 okay, it's there in this direction and that direction, but that's not even a thing, right? So, for unequal elements, they cannot be, for two unequal AB, again take it the contrapositive. What is the contrapositive? So, see, if the contrapositive, so if A is not equal to B, then either AB is there or B is there, both cannot be there, right? So, there is an exclusive OR between them. So, is this reflexive antisymmetric R1? Why not? Because 1 2 is there and also so is 2 1, right? Is this antisymmetric? Because 1 1 is there and 1 1 is there, but it's allowed for equal things to be related in both directions, but not the other side, okay, not unequal elements. Is this relation reflexive, antisymmetric? 1 3 is there, 3 is 1 isn't, right? 3 2 is there, 2 3 isn't, and 2 1 is there and 1 2 isn't, right? So, this is antisymmetric, okay? Yes, sorry? Okay, so what you know what is the definition of antisymmetric? Antisymmetric says for unequal A and B, unequal elements A and B, if AB is there, then BA cannot be there. Okay? Only for equal thing you can say this. Whenever you find two things in bidirectional related, they must be equal. This is what's written there. What is meant by that is only for unequal thing, either AB is there or BA is there or none. But cannot happen that, by the way, sorry, I said exclusive OR, it can't be exclusive OR because none of them is allowed. So, if AB is there, then BA isn't there. That's what it says. Now, in the third one, R3, yes, please. Kaun sa equal? If AB is there and BA is there, so somebody can say this thing. So, here is, if 1 2, suppose this is my relation, right? I will say this is not antisymmetric because 1 2 is there and also 2 1 is there. They are there in the other order, right? In the other, okay? But somebody can say, well, look at this. There is 1 1. Okay? Let's say, look, 1 1 is there in this direction, let's say left to right, and this 1 1 is there also in the right direction. So, how come this is symmetric, antisymmetric? We count as 1, plus it is allowed for equal things to be related in bidirection. Okay? So, the statement says, let's look at that statement. This basically says, if A is not equal to B, then if AB is in R, not R, this R, then BA cannot be in R. Okay, this is the statement or definition, the requirement of antisymmetric relation. Okay. Okay. Now remember this thing. Symmetric and antisymmetric, they are not the negation of each other. We spent quite significant time on that when we did big existential and universal quantifiers, right? You have to be very careful with what is the negation of each other. And that means a relation can be both symmetric and antisymmetric, right? It could be neither of them. Negation for this thing cannot happen. Negation, if one is true, then the other is false, right? If P is true, then Q is false. They cannot be both simultaneously true or simultaneously false. Okay, that's a negation. Here, these properties can both simultaneously hold or both simultaneously not hold or one. Yes, please. If A equals B, if whenever this happens, whenever you see AB is there and also B is there, then A and B must be equal. This is what it says, right? So, only equal thing. I saw AB here. So, let's say A is this one and B is this one. And I also saw BA because B is this one and A is that one, right? But I say, okay, for equal thing it's allowed because you're just writing the same thing multiple times. Okay? Yes, please. Yeah, we're coming to that. Yes, that's exactly the way you should be thinking now. Okay, you have to do this. Actually, we saw example. Let's see. Where is which one is this? Yeah, look at the middle one. 1 1. Is this symmetric? Is 1 1 symmetric? Yes. If AB is there, then BA is there, right? So because the condition isn't met, no AB is there, so then that was why there is no BA, but that's okay, right? So this is symmetric and that's antisymmetric, right? So here is one thing that you are going to construct a few. That we are going to construct some for ourselves so that we really understand this thing. So we have this 4 elements A, B, C, D. I want you to construct a relation which is symmetric and antisymmetric both. Quickly. Yes. Yeah, small one, generally small. Just write AA, right? Write AA or BB, right? It's symmetric, right? Yes. What if I write AB? What if I take the ordered pair AB and that's my relation AB? Huh? Isn't it antisymmetric? It's not symmetric, right? But it's antisymmetric. So what if I make it symmetric? I make AB and BA also. Then that wouldn't be antisymmetric. Okay. So, okay. Come up with a relation which is symmetric but not antisymmetric. The one I just told you. Just take AB and BA. Symmetry, and it's explicitly violating antisymmetry, right? Because you put in AB and now BA also, and they are not equal. Okay. So a relation that is not symmetric but antisymmetric, AB. Just take AB. It's not symmetric, right? Because BA is not there, and it's antisymmetric because BA is not there. Okay. A relation that is neither of them. Yes. Yeah. So AB, BA takes care of the symmetry part, takes care of antisymmetry part. It's not antisymmetric, and AC or AXY or BD, that makes it not symmetric. Yes, please. Somebody was saying something. You could write an empty set for what?
Not symmetric and not symmetric.
So empty set you think is not symmetric? Yes. Sorry, yes, please. Not symmetric. So a relation that is not symmetric. So what is symmetric? Just make it nice. Your problem set. It's make some. What relation is not symmetric? So give me one relation which is symmetric, not symmetric. Just write AB. Why is not symmetric? Because BA is not there, right? So that is not symmetric. But you want it to be symmetric to antisymmetric. You want it to be not antisymmetric. You want the last answer. So what are you asking? Just ask. Can you please? No, let him tell me. It's okay. Yes, please. That's okay. So that's समझ आ गया. What case is समझ आ गया? So what did you want to say? Not symmetric, I told you, right? Not symmetric, you can just write AB. And antisymmetric, you want antisymmetric, so take CD and also DC. Now that is not antisymmetric. Is this clear? A relation, the symmetric and antisymmetric are not the negation of each other. Yes? Is it clear that there could be relations that are both symmetric and antisymmetric, neither of them? These are all the four possibilities. You see, the whole truth table is here, right? All possibilities are covered. So they are not the negative of each other. Okay. Okay, so let's come up with this thing. Come up with a not symmetric relation. It's the simplest, smallest non-symmetric relation. AB. Why is not symmetric? Can you please not do the pen thing? Just have a little, because BA doesn't exist. Okay, so that's it. So we did with the AB pair, we took care of the requirement of the relation not being symmetric, right? Not symmetric. Now, can you come up with a relation which is not antisymmetric? AA, that is not antisymmetric. Yeah, AB, but we already said कि AB and we want to, so CD करो and DC को भी include करो. Now that breaks the not antisymmetry part. Okay. Huh? Okay. So next property is transitive. Okay. A relation is called transitive. It's whenever A is related to B and B is related to C, then A is also related to C. Okay? AB is in R and BC is in R, then AC is also in R. Okay? So the same set, ground set, the domain 1, 2, 3, 4, and R1 is this relation. Is this transitive? Checking transitivity is quite a task. Okay, you will see in algorithm something called transitive closure or matrix multiplication, matrix squaring is actually transitive, checking transitivities. You will see that thing. Matrix powers, matrix exponentiation is the transitivity. When is this relation transitive? Yes or no?
Yes.
Why yes? Why no? Why no? Yeah, no is easy to answer. Yes, why no?
T something नहीं है.
क्या नहीं है?
It's not transitive.
क्या नहीं है something? 3 something नहीं है.
3, it's AB, and this should be like 3,
No, transitivity requires whenever 2 ordered pairs are there, then a third one must be there. So what are those 2 that you are saying for 3, 3? You said 3, 3 is there. This one ordered pair. Where is the ordered pair?
Yes.
Where the first coordinate is equal to the second coordinate of the first ordered pair.
There isn't one.
No, but that's not a thing. Nah. Transitivity is, here is the transitivity requirement. Please pay attention to me. Transitivity requirement is that whenever these 2 specific type of ordered pairs are there, then a third one must also be there. Okay? Understand this. That's why it's harder to check. It's whenever 2 specific types of ordered pairs are there, then a third one must be there. Right? So far all the thing we said it was the one type of transitivity, one type of ordered pairs either it must be there or must not be there, right? Whenever AB is there, then BA should be there. Or whenever AB is there, then BA should not be there. That was antisymmetry or symmetry, right? And the previous first one was whenever AA must be there for all A, right? That was one other condition. Transitivity says whenever these 2 types of ordered pair are there, AB and then the same B, then in the next one appearing is the first coordinate and then some C, right? That C could be equal to A or could be, doesn't have to be equal to A. So then AC must also be there. Okay, so my question is this, does this fulfill that requirement? A, B, C, please. Can you please stop talking? Which are A, B, C? Oh no, they don't have to be in. This B has to be the same as this B. A could be the same as C. Yes? It is transitive. Why?
Because there's 2 pairs like 1, 1 and then 1. Sorry.
You have to check, by the way, all pairs, okay? You have to check all pair. 1, 1 is there, 1, 2 is there, then 1, 2. See, this B, this is B. B and B, they are the same, right? 1 is related to 1 and 1 is in turn related to 2. So then that's why 1 should be related to 2 and 1, 2 is already there. 1 is related to 2 and 2 is related to 2, so 1 should be related, this 1 should be related to this 2, right, which is already there. 2 is related to 2 and 2 is related to 1, so 2 should be related to 1 too, and that's already there. So whenever between these A, B, C you are actually talking about two things, then it's much easier, right? So when it becomes two things, so here is one requirement, 1 is related to 2, if 2 was related to 3, so this one is, so let's see a few which is not, and I'm going to give you more examples for more complex. Is this relation transitive? One example, why not? Yes. 1, 2 is not there. Why must 1, 2 be there?
Because if you have 1, 3 and if you have 3, 2, you should have a relation which is 1, 2 as well.
Yes.
Same thing if 1 is related to
Is there any other flaw, any other problem with this thing which makes it not transitive? 2, 3 क्यों होना चाहिए? 2 is related to 1 and 1 is related to 3. That's why 2, 3 must also be there for this relation to be transitive. So it is that is violated. Okay. So please, yes. 1, 1 क्यों होना चाहिए? 1, 2 होना चाहिए क्यों? Yeah, 1, 2 होना चाहिए. That's the first violation. Please pay attention to this. Please pay attention to this, okay? How many conditions, just simple number of conditions, if I were to ask you, give me example why is this not transitive? Give me different reasons, right? Different counter examples. So you gave me 2, right? You said 1, 3 is there and 3, 2 should be there and those things. How many of them can we make? How many conditions are there for this thing to be transitive? Think about this question, okay? Always think about such question. That's how you should see. You have to check basically essentially all pairs of ordered pairs, right? So the number of pairs of ordered pairs. Do we need to check just the pairs or just ordered pairs of ordered pairs, right? So I have to check AB and CD. I also have to check CD and AB, right? I have to check if the first coordinate and the last coordinate of the two are equal, then there will be some requirement, some restriction on them. It will require some third ordered pair to be present in the thing, in the set. Okay, R3. Is this transitive? Is R3 transitive? Now remember, generally when people read this thing, order is very, set is an ordered thing, right? So we think of this 2, 4 and 4, 3. So that's why 2, 3 should be there, which looks like it's there, right? This order is not important. Okay, I could write this set in many different ways. You have to check for all of combinations of all, yes. Why should 2, 1 be there? Just 1 second. 2 is related to 4 and 4 is related to 1. That means 2, 1 should be there. So this function is, this relation is not transitive. Okay, we saw one counter example to the requirement. Okay, clear? Let's go back to our old counter examples, our old relation example, R1, R2, R3, R4, R6. Okay. Is R1 reflexive? Quickly. Now these are relation own one set, right? Set of integers. Is R1 reflexive? R1 is the less than or equal to relationship. Why is R1 reflexive? Last row people, just please tell me. That white shirt guy. This white shirt guy, yes. What are you? Why is R1 reflexive? Yes, why? The next one. No, the headache guy, the one who was getting headache for the flickers, because of flickers. Yeah, this guy. So is R1 reflexive? Why? A B क्या होता है? A is less than equal to A. You are right, but you have to be able to say it properly. A is equal to B. Yes, next one. Why is this relation reflexive? R1. AA exists करता है for which A? What is A? Yes. For every A, for every A in Z instead of integers, AA is part of R1. Why?
Because the condition says that there is a B that is equal to A.
Which is there is a B.
The membership.
There is, do you see there exists sign here? So why is, yes? सीधा बात क्यों नहीं करते? Why can't you say the thing I want to hear? Somebody just say the right thing, the right keyword. Is R1 reflexive? Why? R1 reflexive, that's the question, right? We want to see why is this true. Why is R1 reflexive? R1 is A less than or equal to B. Is this reflexive?
Just because
Why?
for all pairs A is less than or equal to A.
What is for all pairs? Yes?
For all pairs AA, there exists.
Last one. No? So what is in R1? For all A is in R1, I don't know.
Because B is equals to A.
This is requirement of this. Yes, somebody.
All ordered pairs AA belong to R1.
Yeah, why? That's like saying, okay, what does it mean for R1 to be reflexive? Why?
Sorry, I don't think I understand the question exactly.
So I just, the question is R1 reflexive? Okay, so when is R1 reflexive? You say this thing, this is the format, okay? Well, substitute the word reflexive. Reflexive means for any A in Z integers, AA should be in R1, right? Any number, so essentially 1 should be in R1, 2 should be R1, 17 should be R1, negative 19 should be in R1, right? For all AA should be in R1. Right? That's just a substitution, just rephrasing the question. Is R1 reflexive? So is it true that for all AA is in R1? Why? See, yes. Yeah, because A is less than or equal to A, right? So those of you who said B, the word B is not a thing there, okay? If a number is less than or equal to another number, then those two are related, right? So A is always less than or equal to itself. Any number is less than or equal to itself. Okay. So R1 is reflexive. Is R2 reflexive? No, it's okay. Is R1 symmetric? Is R1 symmetric? Or what did it mean for R1 to be symmetric? Just retranslate, restate. Don't say yes, no answer. Don't give me example or counterexample. Just say, translate this statement. R2 is symmetric. False or true is a different thing. R2 is symmetric. Translate this into a more. R2 is symmetric.
For all A, B, if A is greater than B, then
No,
B is greater
not
than
A, B, English language. R2 is symmetric.
If AB belongs to the relation B.
English. Now this is B. That's reflexivity doesn't require. No? Reflexivity, that every element is related to itself. So that's why B नहीं important. यहाँ पे तो B का बगैर नहीं होता. But don't, very informal natural language answer, not technical answer. What does it mean when I say R2 is symmetric?
So when AB is in R2, BA is in R2.
That's not a technical answer. No, English, Urdu, Pashto answer.
If a number is smaller than another number, then that number is also smaller than
Yeah.
the first number.
So if this basically says being less than or equal to is a bidirectional relation. So if a number is smaller than another number, then the other number is also smaller than this, right? So if A is smaller than B, then B is smaller than A. That is what it means when I say R2 is symmetric. Now, is that true? Not true, right? How would you prove that R2, what am I talking about? R1? R1. R2 is not symmetric?
We use 2 and 3. 2 is
Yeah, you see 2 and 3. 2, 3 is in R2, R1, because 2 is less than or equal to R1. R2 is less than or equal to 3, right? But 3, 2 is not there, because 3 is not less than or equal to 2, right? Okay, is R1 antisymmetric? Is R1 antisymmetric? What does it mean for R1 to be antisymmetric? Translate, R1 is antisymmetric. Just please let this, the one who was just talking, blue shirt guy, let's look at it. Just translate the statement R1 is antisymmetric. Rephrase the statement, don't answer it. R1 is antisymmetric. Just use the definition of R1, it's there on the slide. Use the definition of antisymmetry. No? Somebody else who wants to say something? Yes?
If a number is less than or equal to another number, then that other number can be less than or equal to the first number only if they are equal.
Yeah, so if A is less than or equal to B, then B cannot be less than or equal to A unless B is equal to A, right? So for equality, it's okay that there could be bidirectional thing that both A is less than or equal to B and B less than or equal to A. But other than for unequal number, either A is less than or equal to B or B is less than or equal to A, right? That's what the so-called dichotomy laws or whatever they call it, right? Okay, so R1 is not antisymmetric. R1 is antisymmetric because whenever a number is less than or equal to some other number and they are not equal, then the other number is not less than or equal to it, must be bigger, right? Is R1 transitive? Is R1 transitive? Right? So if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C, right? And it should be there. Okay? So whenever A is smaller than B, if AB is there and BC is there, then AC should also be there. Okay? Because AB is there because it satisfies, let's say, the less than or equal to relation. BC is there because B is less than or equal to C. But then I know equality. Inequality goes like this, right? Inequality is transitive. Okay. So R2 is the greater than relation, exactly the same as what we saw earlier, except for it's not reflexive. Why is greater than relation not reflexive? What would it mean that R2 is reflexive? Yes.
The number is greater than itself.
So no. R2 reflexive, what is the, restate the word? R2 is reflexive. What does it mean R2 is reflexive? Yes. R2 is reflexive. No, stop. Technical, not technical words. R2 is reflexive. What does it mean? No. Yes. R2 is reflexive. No, wrong. Yes. Every integer is greater than itself. That is the statement. No, you said a number. Every number. Every integer is greater than itself. That is the statement R2 is reflexive. Okay, every integer is greater than itself, and that's obviously false. No integer is greater than itself. Even though only one counterexample would have worked, but right now we have no equal positive example. Okay, R3 is R3. What is R3? The absolute value relation. Is R3 reflexive? Is R3 reflexive? Why? Just tell me, just rephrase the word R3. I'm not asking whether R3 is reflexive or not. I'm saying, what does it mean for R3 to be reflexive? R3 is reflexive. Reflexive is a more mathy word, right? R3 is given, the definition is given. Just substitute the definition of R3 and substitute the definition of reflexivity. Just make the statement. I'm not saying whether it's a true statement or false statement or prove it or disprove it. Yes.
Every number is equal to its absolute.
Every number is equal to its absolute. That's a good way. For this R3 to be reflexive, every number should be equal to itself or its negative, which is true, right? What you said is an extra or. A is equal to B is already reflexive. So why do you need? So it's reflexive. Is it symmetric? Is AB reflexive? No, by the way, sorry. Yeah, okay. Is it symmetric? Is A equal to B symmetric? Yes. I'm sorry, is R3 symmetric?
Yes.
Why? Because whenever B is there, meaning A is equal to B, then B is equal to A. But if A is equal to the negative of B, then is B A there? Then B is equal to the negative of A, right? So 2 and negative 2 is there. Negative 2 and 2 will also be there in the thing. So it is symmetric. Is it antisymmetric? Because we just said it's a symmetric. No.
Question. A relation can only be symmetric and antisymmetric if A element of
No.
A.
No, symmetric is a symmetric thing.
आप कहते ना पहले आपने किया सवाल एंटीसिमेट्रिक एंड सिमेट्रिक तो दोनों एक साथ होगा एंड वो तब होगा जब एक एलिमेंट होगा ए होगा उसका क्या रीजन उसका क्या होगा
What was that thing? Antisymmetric and symmetric. So we wanted to make an example of a relation which is symmetric and antisymmetric, symmetric and antisymmetric, right? I just okay, just take this thing. Is this relation, this is now a relation R or R17. Is this relation on this set A, is this symmetric? Yes, whenever xy is there, then yx is also there, right? There is no xy, so there is no yx. Okay? Is this relation antisymmetric? Whenever xi is y is there, then yx is not there, right? Because xy is not there, so yx is not supposed to be there. So we never said that this should be just a or b or a element or one element or something, right? So we just said that. Okay, so what were we? Where were we? Yeah, R5, R3 is antisymmetric. Why not? Because why is R3 and not antisymmetric? Yes.
All it is there.
Give me one example. Now, if you say no, then you just need to, you're not responsible to come up with one counter example. If you say yes, then you have to say for all. Yes.
Because 1 and minus 1 are not equal, but the condition stands.
Yeah, 1 is related to negative 1 and also negative 1 is related to 1, right? Or 1 and negative 1 is in R4, R3, and also negative 1 and 1 is in R3, even though they are not equal. Okay, so R4, is it transitive? If a number is, it's transitive. Okay, if is R4 reflexive? R4 reflexive? Quickly, what is R4? It's equality. So yes, any number is equal to itself. It's reflexive. Is R4 transitive, symmetric? Yes, because no number is actually equal. So whenever AB is AB, for different AB cannot be there. So BA is not there, and that's okay. Is it antisymmetric? Yes. Is it transitive? If x is equal to b, y, and y is equal to z, then x should be equal to z, right? So it's transitive. Is R5, what is R5? The successor. Is it relation? Is it reflexive? Yeah, no number is related to itself. No number is a successor of itself. That's why 5 is not there. So it's not reflexive, right? It's about set of integers. 5 is not an element of R5. 6 is not an element of R5. Is it symmetric? No, because if 5 is equal to 4 plus 1, 4 is not equal to 5 plus 1, right? So 4, 5 is there, 5, 4 is there. A is equal to 5, 4 is there, but 4, 5 is not there in R5, right? So that's why it's not symmetric. Is it antisymmetric? It is antisymmetric because whenever A, B is there, then B, A is not allowed to be there. Okay? Whenever a number is a successor of itself, then y, if y, x is a successor of y, then y cannot be a successor of x, right? That's why either x, y will be there or y, x will be there. Both of them cannot happen. Yes?
अगर हम already prove कर चुके symmetric है and we know A is not equal, A equals B नहीं है. From
Yeah,
symmetric and
please
asymmetric,
don't, you have very strange misunderstanding here. Don't make a whole building on it. Come to me after the class, okay? Clarify these concepts. Clarify these concepts. You're stuck with this A, these are just a dummy variable, okay? Just loop counters. Don't be stuck with that, okay? Understand the examples. Write a few elements of these sets. Always do this. When I give you a relation here or some other set, a function, write 10 or 4 or 5 elements of this relation, okay? And then you will see the patterns there and then answer the question, okay? Take the translation very seriously. It's a meaning when I say R1 is reflexive. Substitute the definition of reflexive, substitute the definition of R1, keep in mind the ground set and make a distance, okay? Make a decision. R6 is, R5 is transitive? No. If A is a successor of B and B is a successor of C, then shouldn't A be the successor of C? No, right? Because A is then the super successor of C, right? That's 2 steps away, 2 hops successor. That's not true. And you can come up with an example. 1, 2 is there, 2, 1 is there, and 1, 0 is there, but 2, 0 isn't there, right? Okay, so R6 is reflexive? No. Why not? Is R6 reflexive? What is R6? What is R6? A plus B is less than or equal to 3. Is it reflexive?
No.
Why not?
You can just take the case where A is equal to 3 and B is
Yeah.
equal to 0.
3, 3 is not in A, right? In R6. 4, 4 is not in R6. Negative 17 is not in R6. Is it true? Negative 17 is in R6. Yeah, but 8, 8 is not there. 17 isn't there. Yes?
It's not always true.
Yeah, it's not true for all A, right? For all elements in the integers. Is it symmetric?
Yes.
Yeah, that's because that's exactly when addition is commutative, right? If A plus B is less than or equal to 3, then B plus A is also less than or equal to 3. Is it antisymmetric? Yes or no? Why not? What would it mean to be antisymmetric?
In that case, they would have to be equal for A plus B and B plus A to be the same.
A plus A, B should not equal B plus A.
A plus B should not, that would require that no. That would require, if this thing was unsymmetric, antisymmetric, it would require that if A plus B is less than or equal to 3, then B plus A is strictly greater than 3.
Unless they're the same.
Right? Unless they are equal, right? That's what it says. So it's not antisymmetric. Is it transitive?
Yes.
Right? If the sum of A and B is less than 3, and the sum of B and C is less than 3, then is the sum of A and C also less than 3?
Yes.
Is it? Really? So 2, 1 and 1, 2. 2 plus 1 is less than or equal to 3. 1 plus 2 is less than or equal to 3. Or let's say 2, 1. So you don't confuse 2, 1 and 1, 1.9. No, it's integers. 1, 4. No, not.
No, then I won't hold either.
So we can take 0, 1. 0, 1 and 1, 2.
Then 2, 0.
No, 0, 2 is okay. No, so what is the first example was good. 2, 1 and 1, 2. 2 plus 1 is less than or equal to 3. 1 plus 2 is less than or equal to 3, but 2 plus 2 is not less than or equal to 3, right? It's not transitive. Okay. Okay. How would you represent relation? Okay. A simple thing. Please. A relation we said is a subset, is a set. let's take a 5-second break and don't move, okay? So remember we said a relation is a subset, right? We know how to represent subsets. How did we represent subset? The computer representation of sets, the bit vector representation or the characteristic vector representation. Please pay attention to me. Stop talking. The bit vector representation of sets, everyone remembers that? Right? Fix an ordering and each bit stands for a particular element, and if it is 1, that element is part of a set, and if it is 0, that isn't part of a set. A relation can be represented exactly by that thing. This is, we'll talk about this in graph theory more in detail of this, it's called the adjacency matrix. Here what we have a relation from A to B, okay. We fix some ordering on A and some ordering on B, right, some ordering. And now we take a matrix, a 2-dimensional table, where one row, there is a row corresponding to every element of A, and there is a column corresponding to every element of B. Okay? Now, if an ordered pair AI Bj is in R1, then in the ith row and the jth column I put a 1. And if some elements AI Bj is not in R1, then in the ith row and the jth column entry I put a 0. Okay? So, here is a good example of this thing. How many elements are there in this relation in R? Right? So, I have a matrix, the number of elements in X is 5, the number of elements in Y is 3. So, I will represent this relation with a 5 by 3 matrix, 5 rows 3 column matrix. Okay. The first row corresponds to the element the element of X called A. The second row corresponds to the element B in X. Then third row is for X, C in X. Yes. Then the fifth row corresponds to E, the last element of X. So we have this implicit ordering on X, and similarly there is an implicit ordering on Y. The columns. The first column corresponds to calc, the second column corresponds to DM, the third column corresponds to prog. Okay. Now, आपका मर्जी है, generally we do it this way, but I did it this way. You can write whatever way you want, but you have to be explicitly clear about it. Okay. Order is extremely important there. So it's a good question. You have to. So the question was, does X always represent, does the number of rows or the rows always represent a particular domain or the first, because Cartesian product, cross product is not commutative, right? X cross Y is not the same as Y cross X. So generally speaking, I think it makes sense that the first coordinate of the cross product should represent rows, and the second coordinate should be represented with columns. But if you want to do it other way around, it's your choice, but you have to be clear. Okay. So now do you know why is this first element, the first row and first column element 1 matrix entry, why is this entry 1? A? Because A calc is in R. And why is the first row third column entry 0? Because A prog is not an element of R. See, it's a simple attendance register for whichever element is there. Exactly the characteristic vector representation. But here we have 2 domains, there we had 1 set, here we have 2 sets. So we just fix some ordering, rows and columns. Is it clear? Some questions. How many ones will be there in such a matrix? If a matrix represents a relation R, what will be the dimension of the matrix? How many rows will be there? The cardinality of the first set, if that's your convention. How many columns will be there? Huh? The cardinality of the second domain, right? How many ones will be there? So the number, how many zeros will be there? Good. Yeah. So the cardinality of the first domain X cross Y the coordinate of x cross the coordinate of y, that is the dimensionality of the matrix minus the number of ones. Okay? Is it clear? How many ones will be in the row, first row? Generally speaking, how many ones will be there in the first row?
Depends on how many
Yes, so it depends on how many what?
elements there are in R, with the first coordinate being from the first row, so whatever that would be, A in this case.
How many elements? So in this case, the first row will represent A, right? The capital A. In generally any relation, how many ones will be there in the first row? Like just describe it in some other way.
Between 0 and the cardinality of Y.
Between that's very good bounds on this. So his answer is it will be between 0 and the cardinality of y. So that's basically saying that in any row, the number of ones could be as many columns as there are, and the cannot be negative, right? So it's a good bound and a good way to think of it. But how many would be there? I mean, just describe it in a different words, right? There's no, we don't have a relation in front of us, so we don't know how many, but describe it somewhat. Not just don't give me a number, yes. Not for this, generally any relation. How many ones will be there? As many? With? Okay, so I think what you meant to say, as many ordered pairs in the relation with the first coordinate is A. Yes? And generally, because of using the word relation, it will be the number of elements A is related to. More strictly speaking, the number of elements of Y which A is related to. In this particular context, it will be the number of courses A is registered in, because A represents students, right, and Y represents courses. So A is a student. So the number of courses A is registered in, if this means course registration, yes? Is it clear? That's how you understand a matrix, in this case a matrix. That's how you understand things. You ask yourself questions. You see extreme cases. What will be the maximum value? What will be the maximum, the extreme shape? What will happen if this is the case? Okay? Just rephrase things and you will things will become clear to you. So here is the relation, the one we saw, the divisibility relation. This is, asked you how many ones are there. I asked you how many elements are there in the relation. Remember, in the divisibility relation, and your answer was 12. Or somebody asked me the question. It was the ICP. There were 12 of them, right? How many ones will be there in this row, in this matrix? 12, right? 12 ones, and the rest will be this thing. Can you represent this matrix, this relation on Q? But just wait, before that, what's the difference between this matrix and this matrix? What's the difference between this relation and that relation? Yes?
This one relation consists of x and y, whereas in other cases only a.
Yeah, don't say consist of. The relation is from x to y, in this case. From the set x to the set y. In this case, the relation is on the set A. Okay, there is one domain, there are two domains, right? They could have the same cardinality or something, right? Yes?
You can say वो पहला वाला explicitly defined है ये
No, both are explicitly defined. Well defined, we constructed it in the previous slide. You are given a formula. A relation is a set. A set can be described by this membership predicate. It could be described by explicitly listing the set of elements. It could be described many different ways. Okay? Both are explicitly, formally, precisely defined. Okay? The difference between them is that is a relation from some set to another set. This is a relation on one set. There is only one domain there. What will be the difference in the matrices? Necessarily difference in the matrices. What times?
This will always be square matrix.
A relation on a set will always be a square matrix. The number of rows will be equal to the number of columns. Can a square matrix represent a relation from one set to another totally different set, unequal set? Yes. But if the cardinalities are the same, then it still will be a square matrix, though the rows correspondence will be different. Okay. So now this will be a relation on a set A. What will be the dimension of the matrix? 4 by 4. Let us say 1, 2, 3, 4 is the fixed ordering. The first row will be 1, correspond to 1, and so would the first column. The second row would correspond to 2, and the third row and column would correspond to 3, and the fourth row and column would correspond to 4. So what would be this matrix, the fourth 4 entry of this matrix?
It would be 0, 4, 4.
Yes. Why? What will be the 3, 4 entry of this matrix? What will be the 4, 6 entry of this matrix? 4, 6 is not an entry here, right? It's out of dimension, out of bound error. Okay, can all of you, did all of you do this? Okay. How many ones will be there in this matrix? 1, 2, 3, 4, 5. Yes, how many zeros will be there? 16 minus 5. Okay. 16 minus 5. No, 16 minus 5. Not. 16 minus 5 is the right answer, the clear-cut answer. I don't want to learn arithmetic. I mean, it's too old for that. Okay. How would this matrix representation of a relation look like when the relation is reflexive? Wait, think about it. Think about it. Don't jump to answer. Briefly. Stop. How would, let's see, so you always learn from incorrect answer, these first attempt answer, right? Those are better. Correct answer is not, doesn't help much. Okay. What's the question? If I have a relation on a set R, what will be the matrix? It will always be a relation. No, I'm just asking this. If I have any relation on a set R, its matrix representation, what will be the type of, what type of matrix would represent this? It will be a square matrix, right? Now, I told you the relation is reflexive, okay? Then what will be the matrix look like? What will the matrix look like? Can you tell me? Yes, you. Yes, the one who just used phone. What will the matrix look like? Huh? Because you're using phone. Yes. What will the matrix look like if the relation is reflexive? Identity. What is the identity matrix? Big words, don't use big words. Diagonals will be?
One. एक diagonal.
The main diagonal will be ones and everything else is 0. So that's called the identity matrix, I guess. All the main diagonal will be 1 and the off diagonal entries, the upper triangle and lower triangle will be 0. Is that true?
It's not necessary. The rest don't need to be 0. The rest don't need to be 0.
Yeah. So why should we impose? Reflexivity requires, what would the matrix look like if
All the diagonals would be
the main diagonals will be 1. The main diagonal entries will be 1. That's what reflexivity require. A should be there. That's now the word should you say in I entry should be 1. It doesn't say anything about ijth entries. Okay? So the main diagonal should be 1 and there could be anything on the left side of the upper triangle or lower triangle. Okay? The main diagonal and these diagonal words only make sense with the square matrix. Okay? Okay. What would the relation look, the matrix look like when the relation on a set is reflexive? What is symmetric matrix? What is symmetric matrix? If ij entry, if the ith row jth column entry is 1, because the matrix is just 0 then 1, so it's both ways. If aij is equal to aji, mji, right? So the jth I entry is equal to ij entry. If one is 1, the other is 1. If one is 0, the other is 0. Now, you said if, that's wrong. Well, it's not technically correct. Right? Yeah, if and only if. So, they are equal. That's what I say. So, that means each row, the ith row is equal to the jth column. Right? Huh?
It would be symmetric about the diagonal.
Yeah, symmetric about, that's called the symmetric thing. That's why matrix is called symmetric. It will be, the upper triangle will be the same as the lower triangle. Okay. Okay. So this was symmetry and the properties of relations. I want to do combining more than one relations, and this is, please pay attention to this thing. Okay, simple. What is the relation? It's a subset of A cross B, as relation from the set A to B, right? So it's a subset, it's a set. We can do all set operations, right? We can take union, intersection, set difference, symmetric difference, whatever you want, right? Complement, all the kind of things. So here is a relation A 1 2 3, B is the set 1 2, and the relation R is 1 2 and 3 2 through 2 order pairs, and the relation S 1 1 2 2 1 2 3 2. Okay. It's a set, right? Relation R is a set and relation S is a set. It's a subset of all A cross B. What will be R union S? We know what is union, right? These are elements of both ordered pairs. So, those ordered pairs that appear in either S or R will go to R union S, right? It's a set in any order. You can write this 1 1 here and this 1 2 there. That's not going to make a difference. What is R intersection S? Well, it's those ordered pairs that appear in A, in R, and in S, right? Those ordered pairs. In this particular case, R intersection S will be 1, 2, and 3, 2, right? And R minus S, R set minus S, what will be R minus set? There is no element, no ordered pair in R that is not in S, right? So, by definition, it will be the empty set. What is S minus R? Not necessarily the same as R minus S. In this case, it's 1 1 and 2 2. Is this clear? You can just do all set operations on that. Where do we need this? Here is a simple example. Please pay attention to this. I have courses, set of all possible courses in Zambil record, right? All RO record, all possible courses offered or to be offered or offered at sometimes, right? Currently offered. Students, and the set of students is all LUMSx CS students, right? Okay, sorry, CS courses and CS students, okay? Not just all course, LUMSx courses. R is a relation which lists all ordered pairs in the format, the first coordinate is student, an element from S, and the second coordinate is a course, an element from the set of courses, and it only lists those pairs if the student S has passed the course C, then SC is part of this thing, okay? And the relation S is those ordered pairs of student and C. If student S, because he or she is a CS student of a particular level, so if S needs the course C to graduate, right? If course C is a required course or a core course or a prerequisite course or something, then those list is there. Is it clear? Okay. So, but this is for each individual, not just a handbook, student handbook, these courses are needed. This is now for each individual, right? It could happen, it does happen, the database store it like this. Remember, requirements of programs change from year to year? Yes? Requirements change for student to students, minor, I mean, so I could have a program which says if you come from electrical engineering background, you are required to take these courses for the same degree. But if you are coming from a biology background, you are required to this other set of courses for that same degree, right? I could have this. It could be different requirement for the sophomores and the juniors and the freshies and seniors, right? It could be different type of requirement. So, R and S, right? Let's see how can we make these set operations and what would they be, what would they signify, right? So, what will be R union S? It will be something, the set of courses which students, the set of ordered pairs where the first element is a student, the second element is a course, right? And either the student has passed the course or the student is required to have passed or to pass the course. this C is required. Right? There will be R union S. That's how we can describe R intersection S. What would be R intersection S? It will be a set of ordered pairs where it will be the pairs of all students' courses which are where the students have passed a required course, right? SC is there in R, meaning it is required, right? It has passed, and SC is in R, S, meaning it was required. So it's a set of all required things, right? What will be R minus S? Just give some word to it. R minus S, more colloquial, like informal way. What will be R minus S? So when the auditor or the academic planning people or academic advisor asks, you say, okay, don't tell me your elective course, tell me what required courses you are done with. That will be R minus S, right? Yes, R is no. So give me the other way around. Give me all the elective courses that people have done, right? To find out which elective courses are popular, which elective courses should be offered more often or should be offered bigger sections. Yes, please, quickly.
Sir, so R union C basically hoga,
R union S.
R union S basically hoga, either student has passed the course or needs the course to graduate.
Yes, either if passed the course or it's a required course. Okay, and S minus R would be. S minus R would be.
Courses that need to graduate but have not passed.
Yeah, so these are the people. This is what mainly academic advisor would be interested in, right? Okay, you come to me for R union S, so it's a set. Now you take union. You know what is a union, right? Now you can give it any word you want. But one way, the way he puts it is these are all the courses that the student has passed, or union is or, right? Or the student is needed will require to pass. So these are actually those things that you ultimately will see if you take the end of the year, the transcripts. If you combine all the transcripts, you will see these courses. Some have already been passed, will appear on transcript. Some are required, so they will. Students will have to take it, and then they will appear on a transcript.
Intersection S would be student has passed the core course.
Yeah, all the required courses that students have passed. Yeah, all the required courses that students have passed. We spent time on it. Now I just want to move first. Okay, so this we will do next time. Okay.